Bismillahirrahmanirrahim. Rabbi Zidni Ilma. Students of DPS, Assalamu alaikum. I am Irum Asghar, SS Physics. Let us revise our previously read article. Energy stored in an inductor. Energy is stored in the magnetic field of an inductor, like energy is stored in the electric field of a capacitor. Here we have a coil connected to a battery and a switch in series. As we open or close the switch, the magnetic field lines passing through the coil change, and thus an EMF is induced, which opposes the EMF of the battery. That's why it is even called back EMF. Now the battery has to do work in displacing the charge against this opposing force, or this back EMF, and this work done by the battery on the charges is stored in the inductor as the potential energy. The equation for potential energy is UM is equal to 1 by 2 Li square. UM is the magnetic potential energy, L is the inductance, and I is the current. For a solenoid, substituting L is equal to N phi by I, where N stands for number of turns, phi is the magnetic flux, and I is the current. Or phi is equal to mu naught Nia, where N is the number of turns per unit length. L becomes mu naught into N square into Ia. As number of turns is equal to number of turns per unit length into length, and magnetic field through the solenoid is equal to mu naught into Ni. Therefore, the equation for energy stored in an inductor becomes 1 by 2 mu naught into B square into Al, where A is the area and L is the length. We can also find the energy density, which is the energy stored per unit volume inside the solenoid. The equation for energy density is UM is equal to 1 by 2 B square over mu naught. Today we are going to study an alternating current generator. An electric generator is a device which converts mechanical energy into electrical energy. We give mechanical energy as input and receive electrical energy as an output. This electrical energy can appear in the form of direct current or an alternating current, depending upon the design of generator being used. Thus, there are two types of generators: direct current generators and alternating current generators. Electric generator is also called a dynamo or an alternator. We prefer to produce alternating current in the generator because electricity produced by this method is cheaper and it can be transmitted over longer distances with lesser losses of energy. It has comparatively lesser cost. The concept of alternating current was introduced by Nikola Tesla. He introduced the first electric generator and told about the benefits of alternating current. AC generator. Definition: it is a device which converts mechanical energy into electrical energy, and this electrical energy appears in the form of an alternating current in the output circuit. Working principle: AC generator works on the principle of Faraday's law of electromagnetic induction. Faraday said that whenever the magnetic flux passing through a conductor is changed, an induced EMF is developed across the ends of the conductor, and if the circuit is closed, then an induced current flowing through the circuit can be detected. This current can be used to run different electric appliances. We can produce an induced EMF by different methods. Every method basically involves a change in the magnetic flux passing through the conductor. We should discuss few methods for the generation of induced EMF. We can produce an induced EMF in a conductor by moving a magnet towards or away from the stationary conductor, and we can detect this current by means of a galvanometer. We can produce an induced EMF by moving a conductor across the magnetic field. In this way also, the flux passing through the conductor changes. Here we have kept the magnet stationary. We can change the magnetic field passing through a conductor by changing the area of the conducting coil or loop through distortion, as shown in this figure. We can also produce an induced EMF by rotating the coil inside a magnetic field. In this way also, the flux passing through the coil changes. We can also produce an EMF by changing the current passing through a coil, as we have read in self-induction and mutual induction. We can also produce an induced EMF through an electromagnet. This conductor has been turned into an electromagnet by winding a coil of current carrying wire. As the current passing through this coil varies, so does the flux passing through the conductor. So in this way, we can change the flux passing through the conductor and induce an EMF. In an AC generator, we choose to produce induced EMF either by rotating a conductor in the static magnetic field, or in commercial AC generators we use a static conductor called armature, around which magnets are rotated to produce an alternating current, which we shall be discussing afterwards. But to understand the working of an AC generator, we rotate the conductor inside a uniform magnetic field produced by a stationary magnet. By some source of mechanical energy, we can rotate the conductor manually by attaching a handle with it and move it inside the magnetic field provided by the magnet. We can even use a fuel engine to rotate the coil inside the magnetic field. Or we can even use a steam turbine to rotate the conductor inside the magnetic field. We can also use a turbine run by a waterfall to rotate the conductor inside the magnetic field, and in this way, when the conductor moves inside the magnetic field, current or induced EMF is generated, which is supplied to the consumers. By rotation of the conductor inside the magnetic field, an induced EMF called motional EMF is generated across the ends of the conductor. Here in this figure we have shown one loop of a conducting coil which rotates inside the magnetic field of the magnet and generates an induced EMF across the ends of the conductor. The ends of this loop have been connected to an external circuit by means of connecting wires. A bulb having resistance R has been attached as an external circuit which would glow due to alternating current supplied by the generator. As the conductor rotates, AC is produced, but a problem arises that when the conductor rotates inside the magnetic field, due to its rotation, these wires connected to the external circuit get twisted. And if they keep on twisting to a certain extent, their elastic limit would exceed, and they would break, and supply of current to the output circuit would be cut off. These wires also act as current leads. One carries current to the bulb, and the other, after supplying electrical energy, carries the charges back to the generator so that they get energized to flow once again inside the circuit. Due to twisting of these wires, high potential wire comes in contact with the low potential wire, and a short circuit results, which can cause fire, which would burn the entire generator and the circuit would collapse. To avoid such kind of situations, we make special modifications in the circuit of the generator. We use slip rings and carbon brushes as shown in the figure, so that the coil keeps rotating inside the magnetic field without disturbing the external circuit. We should be discussing their function afterwards. Construction. Let us now talk about the essential parts of the AC generator. To design an AC generator, we need a source of magnetic field. This source of magnetic field is kept static, that's why it is called stator. An armature or a conductor, which is used to design a generator, and it is rotated inside the magnetic field in the structure which we are discussing today. So, due to rotation, it is called a rotor. A source of mechanical energy would be termed as a mover because it moves the conductor inside the magnetic field. Slip rings and carbon brushes. Now we shall talk about the source of magnetic field. The magnetic field is usually provided by an electromagnet consisting of coils of conductors. In this figure we can see that we can choose a conductor of any desired shape. It is wound by coils of wire carrying current by passing a constant amount of current through these coils. This conductor turns into an electromagnet. The larger would be the amount of current, the stronger would be the magnetic field produced by this conductor. We place an armature or a conductor which is needed to produce an electric current inside this magnetic field. The conductor is mostly placed within the pole faces of the magnet because here the field is uniform. We generally use concave pole faces so that the field produced would become stronger and radial. To produce a large amount of motional EMF, we not only need a strong magnetic field, but we also need long conductor present inside the magnetic field. To increase the length of the conductor, we use an armature. The part of an AC generator in which the voltage is produced is known as an armature. In actual practice, a number of coils are wound around an iron cylinder which is rotated in the magnetic field. This assembly is called an armature. To increase the length of the conductor within the magnetic field, we use a conducting coil of wire wound on a rectangular iron cylinder having end loops or turns to increase the motional EMF. In actual generator, we need to meet the electrical needs of a community, so we use multiple coils instead of one, wound around the same iron cylinder at different angles with respect to each other. We also need a source to rotate the armature inside the magnetic field very quickly, so that the speed of the conductor increases, which in turn increases the motional EMF. To rotate the coil about a certain axis, we use a turbine run by a waterfall which spins quickly, and we connect its shaft with the axis of the armature, which consequently starts spinning with a uniform angular velocity omega. Now we should talk about load. Any circuit or device which consumes electrical energy and converts it into other non-electrical forms due to its specially designed resistance is called a load. In AC generator, load is our external or output circuit. We can see in this figure, these are the pole faces. This is the magnetic field shown by arrows produced by this magnet. This is one loop of an armature coil. This is the source connected to rotate the coil inside the magnetic field with constant or uniform angular velocity. Here load would be connected. In the previous figure we connected an electric bulb. Here we have connected a galvanometer to detect the amount of current generated by this generator. These are slip rings and these are carbon brushes. Slip rings. Slip rings are metal rings used to rotate the armature constantly with uniform angular velocity without disturbing the output circuit. These rings are concentric with the axis of armature and rotate with it. One end of the armature is connected with one ring, suppose we name it as R, and the other end is attached with the other ring, say R'. These rings transfer power from the rotor of an AC generator. Here we can see that one loop of coil is attached with these rings. As the coil rotates, these rings also spin with the similar speed as the coil does. These are concentric with the axis of rotation of the coil. They help in rotation of the coil without disturbing the external or output circuit. It is done by the help of carbon brushes. So we place carbon or graphite brushes placed against slip rings such that these brushes, suppose their names are B and B', they remain static and the rings keep slipping against them, maintaining a constant electrical connection between the internal and external parts of the circuit. We connect the external circuit by means of wires with these carbon brushes. They make sure that these wires do not rotate as the coil rotates inside the magnetic field. Thus, they ensure a constant supply of electrical current to the external circuit. The slip rings and carbon brushes Allow the coil to rotate continuously in the magnetic field without disturbing the external circuit. Now we shall discuss how does an AC generator work. We know that through the change of flux, generator produces induced EMF. Here in this case, this is motional EMF. To understand the conversion of mechanical energy into electrical energy, in the beginning, for simplicity, we consider a single rectangular loop of a coil of armature having area A placed in uniform magnetic field of strength B. In this case, the loop is rotating about z-axis with constant angular velocity omega in anti-clockwise direction, as shown in the figure. Suppose the loop of coil which we are considering is named as A, B, C, D, A. It has four sides: side AB, BC, CD, and DA. AB and CD are indicating the length of the rectangular loop, while BC and AD show the width. Here we are rotating the loop with constant angular velocity omega in the anti-clockwise direction, and the loop is rotated about z-axis. The plane of the loop is making a certain non-zero angle with the magnetic field lines. We shall calculate the motional EMF induced in each side of the loop. This figure shows the top view of our loop. We can see the top end of side AB and the top end of side CD. The linear velocity v of the loop is making an angle theta with the magnetic field produced by this magnet. This is the direction of rotation of the loop. The motional EMF induced in the side AB has a magnitude as shown. The EMF induced inside AB is equal to VBL sin theta, where V is the linear velocity of the loop, B is the strength of magnetic field, L is the length of side AB, and theta is the angle between the linear velocity and the magnetic field strength. As the coil rotates, the motional EMF is generated in the entire loop. The charges present in this length of wire AB would experience a force in the downward direction according to right-hand rule. So they would start moving from end A towards end B due to this force. In this way, an induced current would start flowing through this side. This side CD is also present in this magnetic field. It has same length as the side AB. According to right-hand rule, the charges present in this side of the conductor would experience an upward directed force, and they would start moving from end C towards end D, which means from bottom to the top. The magnitude of induced EMF in the side CD is also VBL sin theta, but here the charges are moving from the bottom to the top. Now we shall talk about the sides BC and DA. The net contribution to the EMF by these sides is zero, because the force acting on these charges is not along the wire. According to right-hand rule, the charges present in the side AD and BC also experience force, but this force makes them move in the upward-downward direction. So they do not drift along the wire from end A to D or from end B to C, but they keep bumping up and down. In this way, they do not contribute in generating the EMF. However, the charges moving from A to B drift them towards the end C, and in this way the current flows through the circuit. The induced current developed inside AB and CD has similar direction, as we can see that the charges start moving from A to B and then afterwards they move from C to D. So generated currents have similar directions. Let us write the equations for the EMFs produced by the sides BC and DA. The EMF is 0. So we can calculate the total EMF as net EMF is the sum of EMFs generated in the side AB and CD. The equation finally becomes 2 VBL sin theta. If the loop is replaced by a coil having n turns, then the total EMF in this coil would be 2n into VBL sin of theta. The linear speed v of the vertical wire is related to the angular speed omega by the equation v is equal to r omega, where r is the distance of the vertical wires from the center of the coil. We will substitute this value in the above equation. Thus our equation becomes 2nr omega bl sin theta. We would write 2rl separately because here 2r represents the diameter or the width of the wire and L represents the length of the wire. Area is equal to length into width, so the area of the loop becomes 2rl. Substituting this value in the equation becomes n omega ab sine of theta. As the angular displacement theta is equal to omega t, so the equation becomes n omega ab sine of omega t. This equation shows that EMF varies sinusoidally with time. We know that maximum value for sine function is 1, so EMF would have maximum value when sine of omega t is equal to 1. Thus maximum EMF represented by E naught is equal to n omega ab. अक्सर बच्चे इसको नवाब भी पढ़ते हैं. This equation can be written as E is equal to E naught sine of omega t. If R is the resistance of the coil, then by Ohm's law, induced current in the coil would be I is equal to potential difference divided by resistance. So the current becomes I is equal to E naught by R into sine of omega t, or I is equal to I naught sine of omega t, where I naught is the maximum current generated by the rotating coil, and it is equal to E naught by R. The angular speed omega of the coil is related to its frequency of rotation f as omega is equal to 2 pi f. Thus the equations of EMF and current would be transformed as E is equal to E naught sine of 2 pi f into t, and I is equal to I naught sine of 2 pi f into t. The above equation indicates the variation of current as a function of sine of 2 pi f into t. As we can see, this is a graph between EMF and time. We can plot a similar graph between the current and time and current and angle theta. As the angle theta or the time changes, the orientation of the loop with respect to time also changes. Initially, the coil is vertical, then after quarter rotation it turns and becomes horizontal. Once again, it turns, completes half rotation, becomes vertical again. Once again, it comes to its horizontal position, completing 3/4 of rotation. Finally, it completes one rotation and becomes vertical again. The EMF generated during this time has been shown. Variation of current according to different orientations of the loop inside the magnetic field. We are going to discuss a graph which shows variation of alternating current as a function of sine of 2 pi ft. We have drawn a graph between the current and the angle theta. After completion of quarter rotation, the angle covered is 90 degrees. After completion of half rotation, the angle covered is 180 degrees. After completion of 3/4 of rotation, the angle covered is 270 degrees. And upon complete rotation, the angle covered is 360 degrees. We are considering only a single loop of the armature for simplicity. Initially, the plane of the loop is perpendicular to the magnetic field, but the angle between velocity vector and magnetic field is 0. As sine of 0 is equal to 0, so initially the current is 0. When the loop turns an angle of 90 degrees, the angle between velocity vector and magnetic field becomes 90 degrees. Sine of 90 degrees is equal to 1, and it is the maximum value of sine function. So the current would achieve its maximum value. Maximum amount of current produced by this loop would be I naught. When the loop has covered an angle of 180 degrees, the plane of loop once again becomes perpendicular to the magnetic field. Now the angle between velocity vector and magnetic field is 180 degrees. sine of 180 degrees is 0. So the current becomes 0. When the loop has covered an angle of 270 degrees, the plane of the loop becomes horizontal and sine of 270 degrees is -1. So maximum amount of current would once again be generated but with a negative sign. We would achieve the maximum value of current but in the opposite direction. When the loop has covered an angle of 360 degrees, its plane is perpendicular to the magnetic field. The velocity vector is making an angle of 360 degrees or 0 degrees with the magnetic field, and sine of 0 or sine of 360 degrees is equal to 0. So the current is once again 0. The graph for current during one rotation of the loop is shown in the figure, and we can see that it varies sinusoidally with the passing time or with the changing angle. The variation in the current is also shown by this slide. Case number 1. When the angle theta between V and B is 0 degrees, the plane of loop is perpendicular to B and the current is minimum or 0. As angle theta increases, the current increases, and at theta is equal to 90 degrees or pi by 2 radians, the loop becomes parallel to B. The current is maximum directed along ABCDA. On further increase in angle theta, the current decreases, and at theta is equal to 180 degrees or pi radians, the current becomes 0, as the loop is again perpendicular to B. When angle theta is greater than 180 degrees but less than 270 degrees, the current increases but reverses its direction, as is clear from the figure. The current enters its negative half cycle and now it is directed along DCBAD. At theta is equal to 270 degrees or 3 pi by 2 radian, the current is maximum but in reverse direction. It is equal to I0 but with a negative sign, and the loop is parallel to B. Case number 6. At theta is equal to 360 degrees or 2 pi radians, the loop is perpendicular to B and the current decreases to 0. One rotation has been completed. After one rotation, the cycle repeats itself. The current alternates once in direction in each cycle. Therefore, such a current is called the alternating current. It reverses its direction f times per second. The current provided by Vapda to our houses oscillates 50 times in 1 second. So its frequency is 50 Hz. Following are a few advantages of AC generators over DC generators. Operating voltage of AC generators can be easily stepped up and stepped down through transformers. Transmission line size might be thinner because of the step-up feature. Losses are relatively lesser than DC generator. Size of the AC generators are relatively smaller than DC generators. This is our assessment for today's lesson. Question number 1. Draw a label diagram of an AC generator. Question number 2. Discuss the working principle of an AC generator. Question number 3. What are slip rings and carbon brushes? Question number 4. Discuss the construction and working of an AC generator.